Alrighty, how's everybody doing today? Awesome. So today we're gonna be talking about torque. Now, before actually we talk about torque, let me actually do a little review about some stuff where we went over last time. So we started this talk about displacement. And what is displacement? It was a change in position. And I'm going to use the x-axis as one. So it'd be like, let's say, change the position in the x-axis. And again, this triangle that's over here, that's your change. So if we do the change in the x-axis, that means we're going from where? We're going from the initial position to the final position. The difference between them, that's your change. So it'd be your xf, and it's your xi, xf, that's your final position. And that's your initial position. Of course, we gave it a letter. Usually we give it a letter D, right? And the most common unit for it is going to be your meters, which is your M. Now, and we give it a letter M. Now, so you take this distance that we're actually going over amount of time, and we're going to give it the letter T. So this is displacement. And what we're going to get? We're going to get something called the my pen is not cooperating here. This velocity. We're gonna give it a letter V, which mainly is your distance over your time. Most common is your meters for your distance, and your time is gonna be in seconds. You give it a letter S. So meters per second. You take this velocity and divide it by your time that you're actually going under. So you're going from one velocity, you're changing from one velocity to another, change the velocity over time, and you're gonna get acceleration. You give it a letter A, which is going to be your meters per second squared. Now, you have this acceleration that you can apply to an object. So let's say you have an object of mass M, and you're going to multiply, you're going to apply an acceleration, you're going to have a velocity V. And that's where you're talking about the force. So the force that the force from Newton's second law is going to be this acceleration multiplied by the mass. How much? That's what you're going to get the force. Now, what is the unit for your mass? And let me actually go ahead and label this. So your M, that's your mass for your object, which is going to be in kilograms. And the acceleration is going to be meters per second squared. So applying both of these, what you're going to have kilograms, meters per second squared. That's what we call a Newton. And you get a big letter N, and that's going to be the unit for the force right over there. And you can actually see this in the following diagram, right? So again, we have an object, let's say of mass M, and that's your M for your mass. And you're moving this object from one place to another to a distance D, right? This movement over amount of time, you're gonna have a velocity. The velocity change from rest, for instance, to whatever it is, from velocity final from velocity initial to velocity final. That's when you're gonna have an acceleration. So your force is gonna be your mass times your acceleration. So by the way, a little technical difficulties. Now let me talk about this force for a second. So this force over here was perpendicular to the ground, but let's say if it wasn't. Let's say you have a force going on in an angle like that. Now, let's say this is your force F. This is going to be a consolidation of all your force in the X component and your force in the Y component. I actually got a better picture going on right now to see over here. Here's the picture. All right. So here's your vector f, and again we said it was a resultant of two components: your f in the your x f in the x component, and your f in the y component. So in this case, that's your f of x over here, and f in the y direction. Now, this is caused by an angle. Let's call this angle theta, and the sine of that angle is going to equal to what? Sine of the angle is going to be opposite of our hypotenuse, right? Which is going to equal to, in this case, your f of y component divided by your hypotenuse, which is your main vector f. So in this case, solving for f of y, what you're going to have? You're going to have your main vector f times your hypotenuse times sine theta. Same thing holds true for, let me get a different color, for your cosine theta. So in this case, your cosine theta is going to be your adjacent to your hypotenuse, which is going to be your f component in the x direction divided by your hypotenuse f. So that means that your f component in the x direction is going to equal to the main vector f hypotenuse multiplied by cosine theta. And that holds true for that. So when we actually talk going back over here, we have this little object that we're actually pushing towards a distance. The end. Let me actually draw this one. This is my object with mass m, and I am pushing it in a force to a distance derived as, like let's say right over here, as a distance d displacement, whatever, from initial position to final position. Notice that's what we're talking about, your work, which is going to be your force that you have, which is the mass times the acceleration that you're having, that causes the object to have a velocity on that side. So your acceleration, which is going to cause to have the velocity from initial to final, is going to be your FD. Now is going in the direction of the displacement. But what if you're going in an angle? That's when you're talking about over here in the fx component, which in this case is going to be your f cosine theta. So here's your f. So this is going to be your f cosine theta because you are going in the x direction. So, and that's what we're talking about work. So when we actually talk about work, we're talking about, let me actually write this down. We're talking about work. We're talking about work. We're talking about when the force is in the same direction as the displacement. Now, supposedly, let's say I have a ruler. This ruler, let's say I put a little nail right over here. I'm going to call this nail the pivot point or the main axis. So pivot point, the same nail. Now, what would happen if I would put a force on it that way? It would rotate this side. What would happen if I would, let me get a different color. Let's say if this is without this force, let's say if I put a force on this side, it will rotate on this side. Correct? Yeah. And that's what we talk about torque. Now, torque is what causes an object to have angular acceleration, which we defined before as your omega over here. Now, We talked about work, which is your force times your distance. Talking about units, let me actually go this. This is your force, which is going to be in newtons. And this is your displacements, which is going to be in meters. Having combined both of these, and what you're going to have? You're going to have a Newton meter, which we define in Newton as kilogram meters per second squared, multiplied by this meter, so you get kilogram meter squared per second squared. And that's what we call the joule, which we give usually a big letter J, which is going to be your unit for your work. Now, when we talk about torque, the torque itself, again, is what causes an object to have an angular acceleration. And this torque is going to equal, again, to your force times your distance, which is going to be in Newton meter. Go ahead and get a Newton. So torque equals force times distance, which is your Newton meter. But you're like, okay, hold up, Malek. You said that the work is in Newton meter was a joule. They're the same as the torque. That's where we're going to have a little difference. No, it is not. The work is defined as the force, and where's my little work slide, is in the same direction as the displacement. So basically, your work is your Ft cosine theta. Your torque is defined as your force is perpendicular to the displacement. Because again, you're going in a rotation moment. So the force itself is going to be perpendicular to the displacement in order for you to go in a rotational moment. So going back to our little fellow here, so basically we are concerned about this y component over here, which we have as your y component is f sine theta. So basically your torque is going to equal to your f times d times sine the angle. Now, your d over here, let's say you have a force. Let's say this is F1. And this is your distance for your F1. This distance to the pivot point, you're going to have a full revolution, which is a revolution defined before as a full circle, 360 degrees. So I'm going to throw this as a miniature one. So this is your pivot point. This is your F1 that we have. And this is the distance of F1. Let me get a different color so the greens are clashing together. This is your F1. And this is the distance for F1. Now, this is F1. What does that look like? It's halfway through the circle. Halfway through the circle is called the radius. So usually it's your F times D. So we're going to take this D out. We're going to put R, which again, R is another form of distance measurement. So that's going to be Newton meters. Now, boom. Let me go ahead and replace this. And put your R as a replacement multiplied by sine the angle between them, because that's the rotation that is going in there. And that's what we just defined. Okay, and that's what we just defined. We defined the torque. Here it is. So the torque is rational force that made the object spin about its pivot point. You have a pivot point right over here. The object, here it is. Here's your pivot point over here. The object is spinning over there. Now, with the torque, when you go counterclockwise, you're going to have a positive. And when you go clockwise, it's going to be negative. So here's your positive. That means you're going counterclockwise. Negative, you're going clockwise. And that's what we need to start talking about equilibrium. Let me just write this down. Equilibrium. Now, when you have an object and you have a force on it, this object, we said, is going to accelerate that object to a different velocity, and it's going to be a different displacement from another. But that's not always the case. An object can be either stationary or in motion. How is it going to be stationary? By having a balanced forces. So you're going to have a force of the opposite direction that is balanced with this force. And really, when you talk about equilibrium, you're talking about, let me just write this down, equilibrium. You're talking about two types of equilibrium. You're talking about static. Let me go to this one over here. And dynamic. And you get a different color. Now, your static equilibrium is when the net force and the net torque on an object are equal to zero. And net torque equals to zero. And the object is at rest. That's like the one we seen over here. I actually got a better visualization here. Let me just bring this up over here. So in this one is a free body diagram of the object. What you're gonna have usually the weight going on there, which is going to be your mass times your gravity, and then you get your normal force, which is opposite, and you get your x forces going in the x direction, and the net positive direction and the negative direction. Now, in order to reach equilibrium, that means your forces, all your summation of the forces have to equal to zero. Your net forces have to equal to zero, which means all your forces in the x direction has to equal to zero, and all the forces in the y direction have to equal to zero. All the forces in the x direction is going to equal to zero. That means all the forces in the x, this one, the positive x, plus the negative x. Writing it. Okay, this is going to equal to zero. Same thing with the y. This is what this says over here. Same thing with all the y forces is going to have to equal to zero. That means all the y forces in the positive direction plus all the forces in the negative direction. And that's going to have to equal to zero. The second one that we're talking about is your dynamic. Let me actually split this up. Now, when we're talking about dynamic equilibrium, is when the object is moving while the net force and the net torque and the net torque are zero. This is when you say the object in a state of dynamic equilibrium. So basically, to reach equilibrium, all your forces has to equal to zero, and all your torques is going to have to equal to zero. So let's look at another example. Let's say we have an incline. Here's a little incline right now over here. This incline so this is the incline over here. This is coupled by an angle theta for the incline. Let's say you have an object that is right over here. Now this object is going to have a mass m. And what's pulling it down is a special kind of force that's called the weight, which is going to be your mass times your gravity. Now, perpendicular to the surface is going to be your normal force, and opposite from it is the perpendicular force, which is going to be the same as your normal force. Now, obviously, this object is going to be, let's say if it's sliding down, that means you're going to have a force going backwards. This force is going to be your friction force. Friction. Let me actually label this normal force. Now, let me get a different color. See this when you connect the lines between the perpendicular force and the weight, you're going to have an angle theta. And this is going to be your parallel force. This parallel force is actually dictating going downwards opposite of the friction. If this parallel force is equal to the friction, which this normal force is going to equal to the perpendicular force, this object is going to stay stationary. I actually got a better visualization. Let's go ahead and share it right over here. So here, as you can see, it's a little smaller. There you go. That's actually better. And this is our object. So this is your object with your mass m. And again, he has over here has a big M. So that's your mass times your gravity, which is going to be your weight. And here's your normal force, which is opposite from it, is going to be the component of the weight perpendicular to the incline. Is going to create an angle theta because it's going in an incline, which between them, that's what you're going to have your component of the parallel force parallel to the incline, which opposite, that's going to be your friction. Now, you're going to have no net force when F1 or the friction force, which is in this case, this FF over here is going to equal to your parallel force right down over here, which is going to be mg sine theta. And again, we explained that because we are going in the y direction. So that's going to be your sine theta because you are sliding down the y direction, which again, your normal force is going to equal to your impelled force. If that happens, you're going to have no net force on the object. The object is going to be in a state of equilibrium. Now, let's look at this little figure over here. So we got this little figure with the guy that is pushing on a little rotating playground wheel. So he is pushing counterclockwise, and under him you're going to have, so he's going this way, but under him there's going to be a frictional forces going the opposite way. Now, to keep this platform, this little round whatchamajig that they use in the playground from actually turning around, again, you're going to have two forces. You're going to, when he's pushing in, you're going to have a pushing force that's going clockwise, counterclockwise, and you get the frictional force going clockwise. So in this case, the summation of the torques is going to equal to your torques in the clockwise, counterclockwise, plus is going to be the torques in the clockwise, but we said if you went clockwise, it's going to be negative. It's going to equal 0. So basically, your torques counterclockwise minus your torques clockwise is going to equal to 0. And again, that's your summation of all the torques that's sitting in there. And if you get 0 what? Newton meters. Let me actually make the 0 a little bigger. 0 Newton meters. And that's when you actually get into the state of equilibrium. I hope you enjoyed this video. Looking forward for the next lesson. If you have any questions, just please contact me. Have a nice day.